Hi, guys. Okay, so now look at this next calorimetry problem, which is again from the OpenStax book. And this is the chemistry textbook, second edition. And we are looking at the problem of calorimetry 5.3 learning check. So here, it's a very interesting problem. We are given the mass of copper, and we are given the initial temperature of copper, and we are given the volume of water and the initial temperature of water, and we are being asked to find the final volume. Final temperature. The final temperature of the water and the copper is going to be the same. Another thing that is known or will be given to you is the specific heat, and that is the specific heat of copper and the specific heat of water. This is known. This for copper is 0.385 joules per gram degree Celsius, and water is 4.18 joules per gram degree Celsius. Now, first thing, the formula that is being used is the same formula that you know for measuring the heat, which is Q is equal to M times the specific heat times the change in temperature. And we know from the change in temperature is T final minus T initial. Okay, and we are being asked to find the final temperature. Now keep this in mind that the final temperature is going to be the same for both the water and the copper. Now, how is this done? First of all, we take some amount of copper, we take the weight of that copper, and generally it's like some object of copper, which is like a little brick or a little cube, or even something around sphere made of copper. Anyways, you take those copper balls and you heat them in water or in something where it really gets very, very hot. Now it depends, what is the temperature of the water and how much the heat the copper can absorb. So that is a specific heat of water. So if the copper absorbs, that mass of the copper absorbs some amount of heat, and its temperature rises. So here we have the increase in the temperature of copper from the room temperature, to the, when it's heated, it's the temperature basically is an indicator that it is hot, how much of the heat is there. And it depends upon the capacity of the object to absorb the heat. Okay, so here we have 314 degrees Celsius of heat, of temperature. That is the temperature of copper. So this is now the initial temperature of copper after heating it. Now you take this initial temperature of copper, the temperature at which the copper is, which is 314, and you dump it in the water. Now water is at room temperature. So the initial temperature of water is 22.6 degrees Celsius. And when the copper is dumped in the hot copper metal, that object is dumped into the water at room temperature, obviously water is going to absorb the heat because copper is releasing the heat. So the heat absorbed is now heat released, and both of them are the same. The amount of heat that is absorbed is going to be equal to the amount of heat released. The only difference is the direction. So the heat is being released by copper, water is absorbing it, and now the temperature of the water is going to rise. So the temperature of the copper is going to fall, but the temperature of the water is going to rise. So question here is, what is the final temperature? Keep this in mind that the final temperature, the dissipation of the heat will continue till the temperature equalizes of the water and of the copper. So the water, there's going to be certain increase in the temperature, and the copper, there's going to be some decrease in temperature. And what is the final temperature when, it's the whole thing is all equalized? So how do we calculate that? Now, here's a very interesting thing. First of all, we were given the volume of water, not the mass of water. So we had to calculate that using the density of water. The density of water is 1. So density times the volume is equal to mass. So density times 390 ml is equal to 390 grams. So this is the term that you will use here in this case, mass of water. So you take the mass of, now you take the mass of copper times the specific heat of the copper, that's the amount of heat that the copper could absorb. We need to find the T final, but we are given the initial, okay? We are given the initial of copper. That is, so you set up the problem like this. write down the based on, your formula. Q is equal to ms delta T. That is T, not delta T actually here, T final minus T initial, because we don't know what the final, we are finding that. Anyways, we are given the mass of water. So take that mass of water and let's just put this in a different color. Mass of water times the specific heat of water, the initial temperature of water, and the T final is what we are looking at. Okay, this is what T final is, what we are looking at. Okay, now let's plug in the numbers. Now there is a certain way this problem is solved. Otherwise it gets tricky, especially because in chemistry, we had to cancel out of the units. So set up this problem in this way I'm showing you. Okay, so as you can see, what we've done is first we have taken the mass of copper and the specific heat of copper, and we have multiplied that with the T final. And then remember that this is a negative number. So this would be a negative a mass of copper times the specific heat of coppers times the T final. Now negative minus multiply by minus is equal to plus. So here the next thing is this negative mass of copper times the specific heat of coppers times negative Ti becomes a positive. So that gives you m.SH.dT. So now you have split this whole thing. And so then in this way, if you do it, then the units cancel out. So same story you're going to do on the water side. But so water side is a positive, a negative number, a positive number multiplied by the negative number will be negative. So here you have mass of water times the specific heat of water times the T final. Then again, mass of water times the specific heat of water times the T initial. So this is how, if you set it up, then the units cancel out. Okay, the rest is we just have to solve it. Okay, so as you can see now, when you place these, numbers, you will see, okay, there's another thing that you need to bring is when you solve it, you need to bring the knowns on the one side and the unknowns on the other side. So we have the unknown T final that we are trying to find, and the knowns are the other, everything else is known. So you bring in the copper and the water T final on one side, and then the initial T water and the initial of the water and the copper on the other side. And as you can see that this is a negative entity, this is negative, and so this will remain negative. So when this T final, from the water side comes on the other side, which is positive on the right hand side, it becomes negative on the left hand side. So just pay attention to these signs, otherwise it becomes tricky. So here is this negative initially, but the water sign, which is positive here, becomes negative this side. On the other hand, when you move this positive of the copper initial side to the left-hand side, that becomes negative. So pay attention to that. And this was initially negative, so this remains negative. So the whole idea now to set it the problem like this is, number one, canceling the units, and second thing is the canceling the units, and second thing is the signs also. So now once you plug in all the numbers, you see that negative and negative become positive, and then negative and negative become positive. Okay, so that's very important. That is why we do this. So we put the copper on one side, water one side with the T finals. This is the unknown. So in general, this whole entity is unknown now. All this is T final, and this is another T final for the water. So this is, and remember that the T final is the same for both of them, because after the copper is put in the cold water, the heat equalizes. Okay, and then here we have the T initial. So this whole thing is known, and this whole thing is known. So when you put in all the numbers, then this is what you get. Okay, so when you plug in the numbers and solve it, you get the 1727.24 T final, and that these units still remain joules per degree Celsius, and then that equals 66,858.49 joules. Okay, so when you solve for TF, these two units cancel out. The joules and the joules cancel out. And then this becomes, degrees Celsius. So your answer is 38.70 after you solve it. Okay, so just follow this thing, the break it up, the problem into this fashion. Then the signs and the units cancel out in this way. Okay, thank you.